Homeboy is recording. Sick. All right. So what is up, YouTube? It's another C tutorial with Arshan. This time we're going over more advanced topics. I realized that I didn't even get to go to pointers in the last tutorials. So we want to do more. We want to cover more so that people actually know what C is and how to do OOP in C, which is pretty important concepts. To be able to contribute to this card, you need to know all of this stuff, which is why firmware sucks, because you have to know everything to do even like a little bit of commitment to the team. It's pretty much 0 or 1. Haha, it's digital, because you either have to know everything or nothing. Anyways, where's the code for this tutorial? I didn't do this for the last tutorials because I was coding it as I was kind of going. But in this one, I pretty much wrote everything from before so that these tutorials are not like hour long, so you guys don't have to watch me in triple speed and skipping through all my jokes. I'll also be making less jokes, hopefully. So code is here. I made a new firmware project for Midnight Sun. It's identical to the old firmware project, except that the projects are not old cars projects. They're new projects. So all the code for the new car will go here. So I advise that you guys actually start doing stuff here. Even if you're like experimenting and stuff, do everything here. Everything is the same as the old car. So like all the make commands, all the debug commands, vagrants, and like all that stuff. It's like nothing has changed. So let's go to the topics. We are going to talk about C structs and then C pointers, and then we're going to get to some object-oriented programming in C. And for that one, I will show you some like example code from Python, and then I will implement the same thing in C just so that you guys can exactly map everything. What for example, object orientation looks in other languages versus C, because in C it's particularly different because C doesn't have inherent support for objects. That's C++ that does that, and C++ used to be called C with objects, which is, or C with classes or some shit like that. Anyways, structs. What do structs give us? Basically, they allow you to group multiple data types, and then you can come up with more complex data types. This is more for kind of like structuring your code. I mean, when you write your C code, you're given, I don't know, like our flash memory is like something about 628 kilobytes. So either you can just write zeros and ones to 128 kilobytes of memory, or you can actually have names for them. So structs is basically like a more complex version of a variable, and you absolutely have to use it, otherwise your code will become a mess. I mean, it's just necessary. So we're gonna see how you declare a struct, and then how you initialize it, and what happens if it's not initialized, and then what if you want to initialize later. These will make sense once I start working through this example. So let's jump into it. I'm pretty sure I have, so what I'm going to do is that over here I have the firmware repository, right? So I'm in this branch, as you can see, and then I'm going to be playing around and like editing stuff in Vim, but if some of you want to follow, you can kind of like play around and edit stuff in any other repository, but I don't think any of you has the firmware XIV repository anyways. So it's going to take a while till you guys set it up, so don't do it, just watch and then follow along later at home. And then over here I'm at Vagrant. You can see like I do who am I. Ooh, Vagrant. It doesn't say Arshan. So if I go who am I, it says Arshan Khanifar, which is me. And then over here, so actually, yeah, so you guys have seen this, you know the drill. It's pretty much in the shared directory in my virtual machine. It's shared between my virtual machine and my host machine being the MacBook. And then I'm going to basically run all of these projects that I made in Linux. So I'm not going to run it on STM32. So as I explained before, we have our build system builds for both the STM32, which is a microcontroller, and then it also builds for Linux. So for the purpose of the demonstration in this tutorial, I'm just going to run everything in Linux, because I'm going to have more in-depth tutorials on running stuff on STM32 later. So here, let's go Vim projects. So what was the first thing I was going to go through was structs. So C structs. There you go. So this is how you define a struct. So well, by default you can just define the struct by itself, but I'm actually doing something called a type def. So you're defining a type. So this is not making a struct itself. It's basically pointing out what a struct of this type will have. So let's say I want to group a whole bunch of data that pertains to something that's conceptual. So like conceptually, a person can have an age, height, name, a whole bunch of other attributes. So I just like, for demonstration purposes, I just like put 3 of them here. And then in main, I'm basically, so once you do type def struct, you are defining this type of this person. So it's kind of like defining a class, but not really, because this is only for all the data. You don't have any kind of like actions here, so you can't like define a method here. Like you can't do like, I don't know, I don't know, void say hi. You can't do something like this here. So yeah, this is what a struct is. And then in my main function, I'm just defining a person Arshan. So that's just me. And then that's how you define it and initialize it. So that's how you initialize is like the syntax that we use. There's like a shit ton of ways of doing this, but don't use those ways because we have kind of like code style guides. So you have to use this way, which is the style guide that actually makes the most sense. Like if you see the other, like C allows you to do a whole lot of stuff like in so many different ways, but honestly, they don't make sense. They're just there for people's code to compile. Oh, I'm actually 23. Jesus, I don't even know my own name, my own age. So person Arshan, and then you can just go dot, and then that attribute value they just like define here, and then equals, and then this, and then comma, and then you can go with the next attribute, and then just initialize all of them this way. So person Arshan, age, height, name, and I just put a semicolon there, and then I'm just using our log library, which is like log.h. Under the hood, it just uses printf. I can just actually show it to you guys. So if I jump to the definition of this, log debug, it uses log, and then log under the hood uses printf. So this is basically no different than printf. So I'm just like gonna print out all this stuff that this guy has. So I'm basically over here showing that how you access a member of a struct. So I've defined this member, Arshan. If you do Arshan dot, and then it's pretty much like any other programming language where you access the members with dots. Like most programming languages are like that. Like Python's like that. JavaScript is like that. Java's like that. So I'm pretty sure it's like standard notation. If your language doesn't have that, that's considered to be a weird language, I guess. So I'm basically printing stuff. I'm putting format specifiers, and then I just like put the actual variable dot, and then the attribute. So name will go here, age will go here, and then height will go here, right? And then I'm just going to return early over here just to like demonstrate what this looks like. So I'm going to do make run project equals, and then I'm just going to, which project is this? C Structs. This, and then platform equals x86. By the way, don't forget to put this platform. If you're running anything in x86, you just do make run project equals this, and then just don't put the platform. If you don't put the platform, this will happen. It says no rule to make target run because your platform is not x86.
Why does it have to be x86?
Because you're only running this. You can only run this project into x86. Okay. So x86 is Linux, right? Okay. So if I were to, for example, add macOS to the platforms that we support, then this platform would have been macOS. But if you pass in platform as STM32, I don't think it actually runs. Let's see. I'm pretty sure it'll fail because I don't have an STM32 connected right now. I think that's what we have. Yeah, it says like there's no such file directory. So there's no rules for STM32. If you want to run something on STM32, you use the command make program, right? Because in that case, you're actually programming to the flash memory of STM32. I could change these scripts such that they would, like make run would mean running on Linux and programming in STM32. But I think this is more explicit. So I'm not going to change it. And I have this YouTube tutorial, so you guys can come to it later if you make a mistake. Anyways, so let's just run this. Boom. So these are like some messages for this whole thing is compiling and all that stuff. But this is the output of my program. Arshan's name, Arshan's age, 23, Arshan's height, 175. So this whole thing makes sense, right? So now let's go back here. So you know how you declare? It's pretty much, whoops. So here I'm declaring and initializing. So what if I remove this? Over here you're declaring, but you're not initializing, right? So what happens if you declare and then start printing out the stuff? What do you expect to happen here?
Old memory?
Old memory, yeah, you probably get some garbage values, right? So let's try it. Boom. See, we compile our code with like so many flags, so all of the warnings are treated as errors. So if you have uninitialized structs, it'll actually not compile. By default, C would compile, but we're using kind of like really hard flags, which is good because these kind of problems wouldn't happen. So if you want your struct to be 0 in the beginning, you have to explicitly set it to 0. And this is kind of like a special syntax for like setting everything to 0. Otherwise, it would be like kind of like this, and then you would have to set everything to 0. Anyways, let's print out if like this is 0. I'm just gonna print out everything, right? So in the case of name, age and height, it's pretty obvious they're just gonna be 0. But what's gonna happen with name? By the way, I use Andrew. Now, what happens for name? Name by default is a car pointer, right? So if I try to print this, what will it show me? So you can see it compiled. This is from like the first line, and this is like first example. This is for the second example, and you can see that it just says null because that car star, if it's set to 0, if you have a pointer that's assigned a value of 0, that just becomes a null pointer in C. So if you try to print it, the console is smart enough to just say this is a null pointer. So instead of printing out 0, it says null. So that's how structs are made and used in C, and we're going to be using them a lot in our projects, and they're kind of like one of the building blocks of just doing anything in object-oriented programming in C.
I have a question.
Yeah, what's
What
up?
happens for the pointer if you don't set it to anything? You don't initialize, well, you don't set it to anything in your struct, but then you still print it.
So let's try it. What is it called? C structs main. C. Okay. What were you saying?
I mean, in the name pointer, like don't. Oh, it's not a set. Yeah, if you don't assign it a value, like you know how you have set all 0.
Mm-hmm.
If you set, say, age and height to 0, and then don't set a name to anything, is it still a null? Or
Let's see. So let's just do 0 here, right? Let's see what happens. Look, it just becomes null. Yeah. So let's see what happens if I just set some like weird like number value, like 53. What happens? It may not actually. It says initialization makes a pointer from integer without a cast. This is pretty cool. Anyways, so that's how you make write programs. That's how you use structs. So let's go to, so what if not initialized? Our compiler in this case just throws an error. What if you want to initialize later? Well, you can just set it to 0. So in this case, 28. So you're saying like, what if I want to make my struct empty and then initialize it later? Maybe like somewhere else in your code you want to like initialize. So you can be like, Andrew.name equals Andrew, right? Let's actually move all of this down here and then see what happens now. Probably should compile. Let me see if oh yeah, I need to return this. Return. Boom. So you can see that the name got assigned, right? So what if I want to initialize my struct later? Well, you can just initialize it later, but just be sure to explicitly set it to 0. Because in general, you just always want your program to have like a deterministic behavior. Hey Keith, how's it going? Yeah, no worries. Sit down, just watch the whole thing. I'm recording this anyways, so you're being recorded. Alright, what's up?
Does do structs always have to have pointers, or is that just for linked lists?
What?
Do you always have to have a pointer in a struct?
No.
No, right?
No. I could, for example, remove this name.
Okay.
So right now, this name is actually a string, which is why I put car star.
Oh, okay.
Right?
Oh, okay.
Because a name is basically a list of characters, and lists and pointers are like, if you have an array,
yeah.
If you use the name of that array solely by itself, that's actually a pointer to a location. Yeah. Any other questions? Can I move on?
If you have a pointer to a char, how come you can put a string there?
Because a string is an array of characters.
Yeah.
An array of characters is a pointer. So, okay, let me show you this. That's good. Good that you guys asked these questions because I didn't plan for this, but I can just like show it right now. Let me just return early here, just like demonstrate. So, let me define a character. Name, and then let me just define an array of characters. So A, R, S. As you can tell, I'm really creative with my namings. Right? So this is an array of characters, right? Boom. So let me actually do car first car equals name 0, right? 21, right? So I have an array of characters, and then I have another character variable that is the first, that holds the first character name, right? Actually, no. Let's do something else. That doesn't work. So what I'm trying to show is that if you use name by itself, so once you have something like this, right, you can get the first item of name using just name 0, right? But name in of itself is a pointer. So not only is it an array, but it's also a pointer. And that pointer is a pointer to the first location of this array. So it's pretty cool. You guys are about to see it soon in the pointer tutorial. Like that's the next chapter that I'm covering. So maybe I can get back to this in that chapter, actually, because it'll make sense more once I get there. All right, so that's just structs. I will explain that thing later. So pointers. A pointer to a variable is another variable that stores the memory address where that variable, so that variable is like the first variable, is stored. So what does this mean? Let me go to the next slide to see. Yeah. Okay. So in your program, when you assign a variable, when you just like declare a variable, your compiler goes ahead in the memory and then just allocates some memory for that variable to exist. And then that memory by default, it will have some like weird value. And then sometimes it gets assigned if it's depending on where in the memory space it is. But I don't want to get into all of those details right now. Just know that every variable that you use resides on the memory, and then the address of that memory is a value that another variable can hold, which is a pointer variable. So how do you get a pointer to a variable? It's basically the ampersand operator. Is this the ampersand? Yeah, it's the ampersand operator. So it's used for getting a pointer. You use it like this. You just put this behind your variable name, and this expression itself returns a pointer. Let's take a look at the pointers file. So so let me just return early here. Return. Okay, so over here I'm declaring a variable, initializing it to 1, 2, 3, and then I'm printing the value of A, right? And then I'm doing address of A, and I'm just like passing ampersand A, right? So let's see what this returns. Let's just change this structs to pointers, and then run it. Boom. So value of A 1, 2, 3. Address of A some mumbo jumbo, which is like some big string. So my computer has like I think this virtual machine itself has 32-bit addressing. So this may be actually a 32-bit address. Let's see. 1, 2. So that's a byte. That's like 8 bits. And then I have 2, 3, 4. So 4 times 8, that's 32. Ooh, interesting. Okay, so this is like your address space, I guess, has, I don't want to count. It's like something about 6 times 4, 24, no, 6 times 8, 48 bits of address. So by default, your computers right now, I think, are 64-bit architectures. So your address space has 64 bits in it. This may be the case that like it's not padding it with 0, otherwise there'd be 2 extra zeros in the beginning. It's okay. Does that make sense? The fact that this is just an address. This is just a number. It's just represented in hex. So whenever you put 0x, that's how you represent hex values. But this is just a number. It's like a really big number. All right? Does that make sense? Okay, cool. Let's go back. So that's the value. That's the address. You get the address with the ampersand. So let's go back to the slide, see what else is here. So how do you declare a pointer? Because you can declare a variable that is of type a pointer, right? And the way you do it is that you just add a star after the data type. So you do data type, so int, star, and then your variable name. And this defines a pointer to that data type. So let's see how that works. All right, so let's return here. So I'm declaring an 8-bit variable, and then I'm putting a star, which means that this is a pointer to an 8-bit variable, b. Yeah, what's the question?
Is that just like an integer of like an 8-bit integer? Is
Yeah.
Okay.
Yeah, so if you do int, by default, this has like, depending on architecture, either 32 or like 64 bits. And then if you do uint 8t, this is more explicit. It says this is an integer that is unsigned. So this u stands for unsigned. And then 8 means that it's 8 bits. So you can do uint 16t or 32t. So powers of 2 or something like that. So I'm declaring this. And then I'm setting it to the address of A, right? And then I'm going to print the value of B, and I'm going to print what's in that memory address. So I'm doing an extra thing here where I'm like dereferencing that pointer. And that's what my next slide is in it, is on. So I can just run this right now. So you can see that address of A is this. Value of B matches address of A because I literally set the value of B to be the address of A, right? And then what's in that memory address? So like let's say you have a pointer and you want to see what is the value that is stored at that address that that pointer is pointing to. And boom, dereferencing a pointer. You just put a star before the pointer variable. So what does this mean? So I have my B, which is a pointer variable. If I put a star before it, this expression evaluates to whatever is stored at B. So we already know whatever is stored at that address. It's whatever's stored in A, right? So it should be 1, 2, 3. So star B means 1, 2, 3. Let's see if that's true. What's in that memory address? 1, 2, 3. There you go. So that's how you dereference pointers. Everything makes sense so far? Questions? Concerns? Okay, good. All right, so what else is there? That's a really important thing. Okay, so call by, this by should be small by, come on. So call by reference versus value. So what does this mean? This was like, I remember when I was in first year, this was asked in almost like every single interview that I had because employers don't really have anything to ask you, so they ask you dumb questions like this. I mean, this is not a dumb question. But anyways, this is a pretty important concept in C. So, like in programming in general. So, C does call by value. And what does this mean? It means that the arguments that are passed to your function, they're actually copies of the function parameters. So, what does this mean? It means that, for example, when you call a function with like 3 inputs, like, I don't know, some integer, like let's say it only has one input. Let's say you call a function with some integer value 32, right? That variable exactly doesn't get passed into the function when it executes. C makes a copy of that variable and then passes that variable into your function. So why does this matter? You're going to see why. So let's say I declare a variable called C, right? And I'm going to print the address of C here, and I'm going to print the value of C before I call this change this function. And we're going to take a look at what this change this function is. It's up here, right? So the change this function takes this value, right? And then sets it to 4, right? And then, oh, sorry, I'm just navigating a little sketchy. Okay, it sets it to 4, right? And then it just debugs it, sorry, it just prints out the address of this value that got passed in here, right? I'm just doing that for debugging purposes. So I initialize C to 0, right? And then I call this change this function, and then I print the value C after. So what should be the value of C right now here? So C is initialized to 0, I call this, over here it gets set to 4, and then I print it after.
Should be 4.
Should be 4 or 0? You think it's going to be 0? Why is it going to be 0?
I was just change it to
You said it was a value, like the language.
Yeah, so this C gets copied here. And then, so what we expect to happen here, let me actually return 0. Boom. So let's run this again. There you go. C before was 0 and C after is 0. Right? So C didn't change, even though within that function I was setting that value to 4. Right? And to debug, like to demonstrate this a little bit better, I'm printing out the address of the location where C is stored, right? And then inside the function, I'm also printing out the address of this value that got passed in, right? And if you take a look, address of C is this long string, and then address of that value inside the function is a different string, right? So these are not actually pointing to the same location in the memory, right? So you cannot change the value of a variable by passing it into a function. In C, you cannot, right? So how would you be able to do this, though? Because this is a pretty useful thing, and we do that a lot in our code base. Well, what you do is, so what you do is that whenever you want to change the value of a variable, you pass its pointer to the function. And then within that function, you can actually dereference that pointer and change whatever value is at that location. So I have another function called change this using pointer. And if you take a look at the function definition, it takes a pointer to a 8-bit integer, right? So the same value that I just made, the same variable that I just made, I just put this ampersand behind it to get the pointer to that value, and then I pass that into this function, right? And then within the function, I'm dereferencing it, right? So I'm putting a star before it. So this means that go to this location and address, and then set that address to 4, right? So previously, I was doing another dereferencing at line 22 here, right? I was saying go to this location and then read whatever value is at that location, that is the address of which is the value of B, right? So this is just for reading from the memory. So in C, whenever you want to read from the memory, you can just have some variable, okay, you can just read from some variable that holds the location of an address by just putting a star behind it, or you can do a write to that location by just putting a star behind it and then putting an equal sign and then some value, right? So it makes sense so far? So C before changing by pointer and then C after changing by pointer. So what do you expect to happen here? So should C change to 4 or not?
Yeah.
It should, right? Okay. All right, so C before, C after. Well, that's this because I probably didn't write to this file. And then let's run it again because that's didn't even hit that line. Okay, C before changing by pointer, C after changing by pointer, right? So you can see that it's before it was 0 and now it's 4, right? Okay, good. So these are all just like the basics. All right, so what's up?
Oh, he has questions.
So are there actually languages that pass by reference?
Yeah, so like in Python, if you pass in an integer, like a value, if your variable, I think if it's a primitive data type, then it's copied by value. But if it's an object, then it gets copied by reference. And if it's a list or a dictionary, then it gets passed by reference.
What?
Reference,
Oh, reference.
which is the pointer. So you can't get a pointer of a variable in like a high-level language like Python. So yeah, it's weird. It's just, I mean, it's not weird. It's just that's the way that it works. People really get a lot of like pointers are a point of confusion because people have a different perception of programming, and it's mostly because they just don't have that understanding of pointers and like what's happening under the hood. They're like, oh, I'm just declaring this variable. Like, where does it exist? They don't know really. It conceptually makes sense. They see the scope and they're like, okay, this variable should exist here, but you shouldn't take that for granted. And it, like when you come to C, you actually realize where your variables are.
One more question.
Yeah.
Why is passing the memory address the same as passing a pointer? Because didn't you just pass the memory address of B in the second function?
Yeah.
And that. So like a pointer and a memory address are defined as the same thing?
Well, a memory address is an address of a location in memory, right? A pointer is a variable that holds a memory address, right?
Oh,
so that variable itself is stored at a different memory address, right?
Mm-hmm.
So that's why you usually kind of name it that way.
Okay.
So pointer is a variable itself. So, and because my memory is 32 bits right now, or like 48 bits or something, this pointer, the size of this B right here is actually 64 bits.
Yeah.
Because it's an address, and my system has a 64-bit address, right? Whereas this A is only 1 byte, or like 8 bits,
Yeah.
right? So it's interesting that the pointer itself is bigger than the value in this case.
Yeah.
But then later on you will have large structs, and then the pointers to those structs will be like much smaller than the size of those structs.
Also, if you change A to something that's greater than 8 bits, like say like 9 million, it would just break, right?
I don't know. You can try it. Yeah.
Okay.
Yeah, I mean, I don't like you can try a lot of different stuff to get there. Like if you're interested in seeing different errors, you can just get on an existing code base and change stuff to see what happens, which is amazing, by the way. It's an amazing thing to do because you got to know when your program breaks. So it's actually good to play around with these stuff. So we got here, and then structs and pointers. So I initially defined structs, what structs were. So they're just more complex data types. And then you have pointers, which is pointers to those data. And then you have structs and pointers. So you use these in conjunction a lot. And soon we're going to get into OOP. And you'll see why we use them a lot. So never pass structs as arguments, because C by default goes ahead and copies that struct, which is a bad idea, because struct in of itself, if like your program, you're using some object that's like has 7 levels of abstraction, that object actually becomes like pretty bulky. And if you just pass that object, yeah, it just copies it. By the way, what if you want to change that object when you're passing it into that function? You will never be able to do that. Because you're passing by value, right? So almost all the time, we usually pass our structs as pointers to those structs, right? So yeah, it's just something to keep in mind. And then, yay, we get to object-oriented programming. It's like the buzzword you hear everywhere. So it's basically a programming paradigm. There are multiple different programming paradigms. There's functional, there's procedural, and then there's object-oriented programming. It makes a lot of sense to kind of like go ahead and read about these stuff, to like, well, at least the alternatives, to see what else is out there. For example, in functional programming, you don't have state, so you can't store variables, which is pretty sick because like, how can you not store variables when programming? It's weird. But I mean, you can store variables, but they all only exist within the scope of the functions. And you know, it's good to kind of like take a step back and see what you're doing, because most of you guys have only probably done object-oriented programming or procedural programming. So it's an interesting thing to think about. So the idea behind object-oriented programming is pretty much a way to write your code such that it makes sense. So usually we write software to model concepts that are either in our minds or they actually has physical presence, right? So you, for example, to control a device, you can make an object of that device, and then you can implement all these methods that are specific to that device. So, you know, it's a way to structure your code such that it makes sense. And it's used a lot, pretty much everywhere. Software engineering has changed a lot just because of object-oriented programming. So let's get into it. Your program deals with data, and then we have structs. So we've seen structs. You can group multiple data types together to make more complex data types. And then you can have methods. So methods are basically functions that deal with that data. So you want to find a way to kind of put your data that are pertaining to like a concept and the methods that deal with that data both in the same place, right? And the way other programming languages do it is by objects or being able to define classes. So yeah, and the last bullet point is basically, it's a really good way to conceptually structure your code. So I'm going to show you an example of a project in Python, and then I'm going to re-implement the very same thing in C, and then you guys are going to see what's similar. You guys are going to witness what's similar between the two. And I think it'll be very useful to kind of look at it that way, because objects have existence in other languages, but they don't have existence in C, which is why people often get confused. So I'm going to just do this demo in Python. Okay, so let me just make a test. Okay, oh nice, I have this. So actually, let's make it a different page right here. So let's take a look at person.py. So this is a class that I've defined. It's a person. So it's the same, similar to that struct. It has some attributes, right? And in this init function, you can set those attributes. Self, in this case, refers to the object. So a class is a blueprint of an object, or rather, it's a factory of objects. So the initialization method is basically the method that gets called every time you make a new instance of that class. And every time that you call it, this self is the value of, the pointer to that object. Anyways, so we do self.name, name, self.age, age, self.height, height, and all that stuff. And then we do something like say hi, right? So hello, my name is this, and then you can get the height. You can get height in meters. The only reason I put this meters is because I wanted to show you an example of a private method. So this convert to meters. Well, Python allows you to call private methods, because I'm calling it down here to see if it complains to me. Maybe the newer version of Python will complain, but in Python, by convention, if you start any function with underscore, that is meant to be a private function. And I will explain why that matters actually. But yeah, so you have your public functions. So you can call say hi, you can call this, this, and this. And then you have your private functions that are meant to be used by your object itself, but to the outside world, they don't exist. Or to the outside world, they should not know that these functions exist, because that is the implementation of this object. So most of the time, you write code that will that other people will use, right? And when other people are using your code, they only care about the API, or like the interface of your code with their code. So their code will call your code's functions, right? long as you keep that interface consistent, you can go ahead and change the implementation of your code under the hood, but your code will still interact with their code. But for example, if some other code is calling this get height centimeters, and then in my new version of my code, I will go ahead and change this to get height, right? Their code will break because it tries to call get height centimeters, right? So this is important because you want to make sure what is public about your class, and you always want to keep it consistent especially when you're writing libraries. Otherwise, you would have to go to the rest of your code and make sure that it doesn't break. So having defined this person class, I can just come here and create a person. So Arshan is person, and I just like pass in all these variables, and then I call it say hi, height before growing up. Oh, I have like a grow by centimeters. It's like a method that makes that person grow. I wish I could do that in real life, but but Arshan.grow by centimeters, and I just like print the height after growing up, and then height after growing up in meters, and I just like get height meters, whatever. And then I'm gonna call the private function. I just called the private function when I was first writing this just to see if Python allows me to do it, and apparently it does. Test. There we go. Python person. Hi. There you go. So you see all these stuff, right? Oh, it selects both sides, but this is the stuff that are kind of like I want you guys to pay attention to, right? So that's how you pretty much have an object, right? Which is a person in this case. That person can have attributes, and it can have methods that work on those attributes, right? Does this make sense?
I don't use Python, but it's self like your class name basically.
Self is the object name, it's not the class name. Yeah. So whenever you make an object, that self points to that object. It doesn't point to the class.
Yeah.
And there's a difference between the two. Yeah.
What's the difference between the two?
So basically, if I, for example, like one way to kind of like exactly show it with a concrete example is to, if I had, for example, if I were to subclass this class and then have another class that inherits from this class, the self method in that class would point to the object that got created. And then when you're doing like an example of polymorphism, you can treat, because both objects are of the same type, right? You can call all the common functions that they have, right? But within that common function, that self will determine which object exactly you're pointing to, right? So up here, if I do def get class name, let me actually show this here. And then I'm going to do print self class dot name. Right? So whatever there is this function, this will this object, it has this kind of like magic variable. They call it magic attribute, and then it has like, you can get the class name of this object, right? So if I call Arshan dot, let's just call it down here, Arshan dot get class name, and now let's run it. You can see that it's person, right? But what if I subclass this class, right? So I do another class teacher person, right? So this is an empty subclass that just subclasses this person class, right? And then I make another person called, I don't know, like Andrew again, equals teacher, right? And I call Andrew dot get class name, right? So over here, this self variable, right, is within the body of the person class, right? So if I call this self, and call this method on this teacher object, what do you expect it to print? Do you want it to print person, or do you want it to print teacher?
Wanted to print teacher.
Teacher, right?
Yeah.
Because this self is an object
Yeah.
right? It doesn't point to the class of person. Because if it was pointing to the class of person, then this thing, like self.class, would have been a person, right? But if I do python person.py, I just have to pass it the same parameters. So Andrew 19, I guess, and then 170 maybe. I don't know what your height is. This is not like, wait, let's change it to not Andrew. Not Andrew.
Thank you.
Not Andrew. Okay, good. All right, there you go. So if I call get class name on not Andrew, it'll give me teacher, right? So that's basically the difference between an object and a class. So that basically just points to that object that just got created. Does that make sense? Yeah? Okay, good. That was a really good question. I was trying to get away from it by just like being like, no, they're different. And then you ask like, well, what's the difference? And I'm like, oh, fuck. I have to like actually look at the example, think of an example. But yeah. Anyways, this will actually, it's interesting. This is one of the rare cases where you like switch to C and everything's actually kind of more clear. Whereas like previously I used to think that C was the weird language, but to me right now C is actually the correct language. The rest of the language, yeah, C stands for correctness. But yeah, so let's take a look at the same example. So I made a project called OOP example, so that's where it is. So as you can see, let me actually go to projects. OOP example. So every project that we have here has source files, test files, and include files, right? Source files are your .c files. If I do ls source, shows me the main.c and person.c. If I do ls inc, it'll show me person.h, because every single class that you make, it's basically in C we also call them modules. So this is a person object or person module. Sorry, person class or person module. It's not actually an object. Once you instantiate it, it becomes an object, right? So, whoops, let me actually get out of here because I want to have access to the entire project. So OOP example, I want to take a look at person.c and then person.h. So over here, this is how you define your class in C. So you define a file with the name person.h, right? Similar to how in other programming languages, usually the best practice is to have a file for every single class definition. You usually don't define two classes within the same file. A lot of the style guides usually want you to do that. In Java, it's the case. In Python, it's definitely the case. Even in JavaScript, people do that. It's just good practice. And if someone takes a look at your code, it's easy to understand because it's modularized. It's composed of objects in each classes, and each class does exactly what it's meant to do. So here you can see the initial struct is here, and then I'm defining all these methods, right? The user of this class will have to instantiate a struct, right? Possibly initiate it to 0, and then it would have to pass it into this init person method, right? And what they do is that they pass the pointer to that struct as the first argument. If you notice, the first argument for all of these methods is person star person. This kind of mimics exactly what happens in Python, because in Python, the first argument is self, which is the object itself, right? So now it's starting to kind of make sense. And if you take a look at any of our libraries, they exactly follow the same paradigm. The first parameter to all of our libraries is actually a pointer to that object of that library or that object of that module. So over here we have init person, right? So please note that the .h files are your API, right? So by reading the .h file of a library or like some module, you can exactly see what that module does. So, whoops, sorry, got emails. Oh. person.h, okay. So now these are all the declarations of your functions, and these are the declarations of your public functions, and these are the implementations of your public functions. So usually you should only look at this file and exactly know what to do with that library. Only when you have a problem do you go inside that library and see what happens. But usually you should be able to just read the .h file and have a pretty good idea of like how to use that library. Because reading the source code of something doesn't really teach you how to use it, right? You don't have to reverse engineer like a car to be able to drive a car, right? You just kind of look at it and like play around with the user interface, which is this part of it, right? All the parts that are public. You never look at the inside of your engine to be able to drive your car, right? So that was actually kind of a good example. I'm such a good teacher. Over here in Python, if you remember, we had this convert to meters method, right? In C, we have this naming standard where you prefix it with PRV, standing for private, stating that this is a private method. So if you include this person.h file in a different file and then start calling private convert to meters, it tells you that it cannot find it. And the reason for that is because I've put this static variable before, static keyword before this, before this method, right? So, oh, by the way, you can see that person is not getting passed to this private function because this private function, all it does is that it just divides height by 100 and then returns it. So, I mean, similarly, I could have taken person and then return person, like arrow height. Oh, by the way, did I explain this arrow pointer? Ah, I skipped it, didn't I? Let's see. Where did I was supposed to show you like a arrow pointer. Oh my god. Okay, let me actually go back and talk about actually it's not that big of a deal. So we have, let me just go over this real quick. Struct, passing structs. Oh yeah, this was that whole part that I kind of skipped. So structs and pointers, don't pass structs as arguments, pass their pointers in. And then I had this example where I was going to show you how to initialize a struct. So let's say I have this person struct that has like these attributes, right? And then I want to initialize it later. So I do person artian and I initialize it to 0, right? And I want to initialize it later, and I want to do that within a method because you always want to do things in a method. And then, so I have this init person, and I'm passing that person object and all of these stuff, right? So over here, I'm going to set the person's age to age, right? And then there's this weird notation that I'm going to explain right now. The whole reason that I have this section is to like just explain this weird notation, like this arrow notation, right? So I could do person.age and then get the pointer of that, and then this person is a pointer to a person, right? So I can dereference this pointer and then .age and then set the age to this, right? So let's try and see if this works. Make program, make run project equals, and what did I name that? Passing structs. Oh yeah, because you're passing structs as pointers. And then platform equals x86. There you go. So I intentionally did that because it says person is a pointer. Did you mean this, right? So what C is trying to do is to do this first, then take the dereferencing. So one way that you can get around this is to use it like this. So once you put something in parentheses, C will execute that first, right? It's kind of like when you are doing arithmetic and whatever you put in parentheses happens. Bedmass, yeah, it's C follows bedmass. So you can dereference this person, right? And then .age and then age, right? So let's see if this works. So you can see it works because I'm initializing the person's name, age, and height, and I can print them, right? So nothing has a problem here. So the alternative, because this looks pretty ugly, you don't want to have a lot of parentheses in your code. So this notation is solely defined for that, right? This arrow notation. So whenever you have a pointer to act, so whenever you have a struct pointer to a struct, to access a member of that struct, you can just do that struct and then arrow and then that attribute name, right? So for age, I'm doing it the conventional way that you guys just saw, right? But for these two, I'm going to do them using that arrow pointer, kind of like that arrow notation. And you can see that it works because it updated those values, right? So past this point, we're always going to use this arrow. If you take a look at the libraries, they only use the arrow because it just looks better. So, sorry. Let's go back to the Python demo now in the C demo. OOP example, and then we have person.c here. So same init person is pretty much provided here. So if you take a look, person.c and person.h are kind of our like pattern for having an object in or like a class in your code. And how do you use this person object? You do it this way. So you go to main, so OOP example main. So over here you can see that I've defined a variable person, and I've defined this as a static variable. And the reason for that is that because static variables will persist throughout your program. So once you exit a function in C, all the variables that were within that function get dereferenced, like that get freed from the memory, right? So if you have, so you never should use global static variables in your program unless for like as one struct that contains all the data within your program, like 1 or 2 structs, and not much more. And if you take a look at the rest of the projects within the car, they actually look like that. Let me actually show you an example of a really complex project in the old car. So this is the firmware project. So this is the old car, and then XIV is the new car. So if you take a look at, I don't know, chaos, for example, this was a really big project. So this is, oh my god, look at all these includes. But in this entire project, there's 3 static variables. Can storage, emergency fault storage, relay retry service storage. If you take a definition of these, take a look at the definitions of these. These are like big structs, right? Well, this ends right here. I mean, it doesn't even end because it kind of like goes down this whole rabbit hole of like so many different structs. So struct members can be structs themselves, right? And then look, oh my god, right? So you can go like many levels deep, and that's how our code has been implemented, right? So what was I saying? So yeah, in your program, you only usually use like 1 or 2 or 3 static variables, not that much more, because static variables are usually like global static variables are you can change the state of them at different parts of your program, and if you use too many global variables, your program becomes really hard to manage, especially over here where you have interrupts and things are running out of sequence, so you don't really know how to debug it. So for now, just take that as a piece of advice. Usually it'll start making sense more as you start writing code for the car. So now I'm just gonna use this function, How
is making static different from just declaring like your variable globally? Is that exactly the same thing?
Declaring static puts your variable in a different memory location.
Oh.
So it actually goes into your heap instead of stack.
Mm-hmm.
Yeah, and there are many other benefits to using static, or like many other reasons. The static keyword can have many different meanings. If it comes before a function, then it makes that function private. If it comes before a variable, then it makes that variable a heap variable. And then if it comes inside a function, it becomes a heap variable that's used as a counter for like how many times that kind of function got called. So it has many different interpretations, and you can just look it up online to like see what static means like in all cases. I just don't want to confuse you guys because you don't really need to know what static means in every single context. The only cases that you guys care is when you define a static variable like in the beginning of your program to store all of your program in it. And then the next case is when you're defining a private member. So person.c. So over here, static, right? Yeah, that's it. What's up?
So I don't know if you're gonna get into it later, but could you give us like a quick overview of what the chaos library does?
Chaos is not a library, it's a project.
It's a project?
Yeah, it's a project. And chaos is the power distribution of the previous car, and it's a pretty complex project in of itself. It will be useful to go through one of the old cars projects to kind of make sense of how a whole project has been put together. I wrote the lights code, and the lights code uses a lot of different parts of the old project, and it's like it uses a lot of libraries, and it's going to be really beneficial for you guys to actually know how the old car's lights worked, because you can start writing your own projects from there and use that kind of as a template. But I will do that in a different video because that's its own beast. Right now, I just want to make sure that you guys understand pointers, structs, object-oriented programming, because these are kind of like the basis. If I jump to the lights code, it's not going to make sense right now. I mean, at this point it might, because we're like almost halfway done, so it's good. So as you can see, I can create this arson person, right? And I initialize it to 0, and then I call init person. Oh, why don't I call like more stuff here? Because it has like the same behavior anyways, right? So as you can see, I have a person.h file and a person.c file, and then in the person.c file I include the person.h file, and this is pretty important because why is it important? Actually, I don't know if you have to include it here, but it's okay. I'm just going to include it because usually I like to include all of my libraries in the .h file and then just include that person.h file in the .c file, so that in the .c file you don't have to like re-include everything. By the way, there's this really useful tag called pragma once, and what this does is that if you include this person.h header file, and then this header file includes another header file, and then at the end all of these header files include all the standard libraries, right? So you are actually including the standard libraries like multiple times, right? So this pragma once make sure that a header file only gets included once. So to read more on that, you can just like read online. I just wanted to just cover it. If that didn't make sense, just Google it. It's like pretty simple concept. Sorry. Yeah.
You said the person.h is a module, or?
Yeah, a person is a module. So it has person.h file and then it has person.c file.
Oh, okay.
Yeah.
Okay, perfect. So like the combination of the two is the module.
Yeah.
Okay.
If you only write the person.c file, then you wouldn't be able to really include it in this project because you usually include .h files.
Right.
Right? And if you only write the person.h file, then it wouldn't have any implementation, right? Yeah. And that's how you include this. Like if you write an object and you want to basically use it in a different code, like different part of your code, you would have to include it, right? So over here, you can see that I've included it. And then I just declare this variable. I just set it to 0, but you don't really have to. I think static variables by default will get set to 0. And I initialize it, and I just do log debug just to make sure that this init function worked properly, right? And then I can do other stuff. I can, for example, let's say call say hi. So you can call say hi, whoops, and then pass in the pointer to my person struct, right? So let's just change this to oop example, and then now you can see pragma once in main file. I guess you would have to only include it in the header files. That's why I think pragma once in main file. Let's just include it in here. Maybe that'll do it. that doesn't do it. I don't know. I'm just gonna remove it. What? Oh, that's because I didn't save this. Okay, okay. Let's see if I can still put it back in then. Pragma works. Okay, this is saved, this is saved, this is saved. Please work. It works. Okay, good. You can see that it's working. And then, hello, my name is Arshan. Yay. That's because I forgot to put the new line character here. If I put the new line character, it'll print it on a new line. Let's run it again. Boom, you can see this, right? Does that make sense? You may be wondering why these are on a new line and then this one is on its own line. Well, that's because I put a new line character right before I printed these, just for like brevity or like nicer. So if I put like a new line character right before this, it would appear on a new line. Let me just show it to you because it doesn't take that much time. Oh my god. Okay, there you go. Make sense? So it appeared on the new line.
What are the names of the 3 files you have? I know you got person.h and you got what, person.c and
yeah, and then I got main.
Main? Okay.
Yeah, so in my main
how
file.
How are the person.c and the main.c? How are they working together? Like, how are they interacting?
In main.c, you include it.
Okay.
Right? You see up there, I'm doing include person.h.
Yeah, the .h.
Yeah.
But what about the person.c? Do they interact at all, or is it just?
They do, yeah. Person.h defines all the functions. Person.c implements them.
Okay.
And then in main.c, you just only have to include the header file. Because the way our scripts are written, they basically look at all your C files and all the .h files.
Okay.
And then they match. For example, they say, like that's what a compiler does.
Yeah.
The compiler basically compiles this and turns it into object code.
Yeah.
And then it has like a symbols folder or like a symbols section.
Mm-hmm.
So all the variable names or function names that it can find, it'll put them there. And the ones that it cannot find, it'll just keep them at the symbols table. And then you have another part of your compilation, which is the linker. And then the linker, looks at all of your object files, and then if there's like an undefined symbol in this one that's defined over there, it'll link them. And then the output of all of that is an executable that you can execute.
So like, what kind of like if you were to write like what kind of interaction do you want between them? Like, say if you had a function in like the person.c or something,
Mm-hmm.
or like I don't know. I guess I don't really see how they would be tied together. Like
They're tied together because I'm including it.
No, I understand that they are tied together, but I don't understand like how they would interact together in like an actual implementation of a program. Do you know what I mean? Like,
Well, I mean, you just include that piece of code in your main code because
Okay.
main is the one that runs all
Yeah.
the time, right?
Yeah.
Main is kind of like a special name here.
Okay.
I mean, you can change this main to something else, by the
Yeah,
way, if
yeah.
you change your linker script. But main is the one that executes,
Okay.
right? So the rest of your code will be included in
the
main.
Okay.
And that's how you're kind of like, main is the origin of your entire program.
Yeah.
And then everything else that your program interacts with comes to main because main has to include them.
And libraries have to go into Inc, and then C files have to go into SRC.
Libraries, no. Header files go to
Header
Inc,
files go to Inc.
and then C files go to SRC.
Yeah.
Yes, and test files will go to test.
Okay.
So we'll get there.
Cool.
So you guys see the example in C. So now that brings us to modularized code. So code must be composed of modules. In other programming languages, they're objects, or like technically classes, right? Once you instantiate them, they become objects. In C, we mostly refer to them as modules. And the reason we call them modules and not classes is because classes have like other attributes that you don't really get in C. For example, in classes, you can do inheritance, you can implement an interface, and all that kinds of stuff that object-oriented programs have. In C, you would have to kind of do them manually. So in C, you just call them modules because it's really a module, right? It's really like a component of your code that does something. And each module must do something simple and do it well, right? So as an example, in one file, you should not schedule timers, change LED lights, talk to some sensor all in one place because this becomes a mess. And then, your code must be fairly simple. Like every single file should only do one thing, right? So if you take a look at the code for our old firmware project, it was exactly like that. And that's why like going through the code base is really easy. Every single file is like less than 100 lines of code. And for every single module, you have a test file. And then by reading that test file, you can exactly understand how that file works. So I'm gonna walk you guys through like one of our libraries to see how that actually comes into play when you start using our libraries. So, and learning more, please go read about OOP on your own. It's, you can't really learn object-oriented programming by reading a book, and you can't really learn it by just writing programs. You should write programs, gather some experience, go read a book, and then come back and write some more code, and then go read a book. So they complement each other. And you go to a co-op, in that co-op you learn a lot from your coworkers, and then you come back, you write some stuff. Just always be on the lookout to like how to learn these stuff, because it does not come overnight. So our modules. All of our projects and libraries have been written using the same pattern. So I'm just going to show you an example, for example, of our firmware project, especially the old cars firmware project. Let me just make a new pane here. Actually, over here. So if you go to libraries, and then some of these libraries are written by us, some are not. So this MS comment, for example, is written by, like everything that's prefixed with MS, actually. Everything that's prefixed with MS stands for Midnight Sun, is our libraries. So in common, you can see it's exactly just like any other project. It has inc, source, test. If I do ls inc, you can see these are all the different libraries that we can use. So within your code, you can include any one of these files, and it'll work. Yeah.
What's the difference between a library and a header?
A header? No. A library is C code.
Okay.
A project is C code. A header file is a header file of some C code, right? So your library is the common part of your code that multiple projects use.
Okay.
A project is a part of your code that is it doesn't have anything that gets used elsewhere. Otherwise, if it is getting used elsewhere, you would have to like abstract that into a library so that both projects use that, right? So the reason we have libraries is because we want to reduce code duplication, right? Because you don't want to reinvent the wheel every time that you're running a project, right? Saves a lot of time. So, so you can see like all of our libraries. So let me actually show you, for example, GPIO. So as you can see, this is basically a GPIO module, GPIO.c, right? So every single header file, you can just read the comments. The comments are usually really useful. So when you write your own modules, you would have to like write comments like this for your modules. And you can see that object-oriented pattern here. You have your object struct, so GPIO address. So to represent a GPIO pin, you pretty much need the port and the pin. And then there's like a whole bunch of other structs that define the inputs and the outputs of your functions. So when you're talking about GPIO, you usually have states, so state low, state high. All of these are enums. So you never pass in zeros or ones to your functions, because those would be kind of called magic numbers or magic names, which are bad. You always want to enumerate everything, like use enumerations or other kinds of stuff to make your code more readable. So let's see, and then there's, for example, in this case, you have a settings object as well. So in this case, you may have two structs to represent the same module, right? So when you're initializing a pin, you would pass in both the settings object, or sorry, the settings struct, and the address, right? So that's a paradigm that we're using right now here. So it doesn't exactly follow OOP, as you guys saw in like Python. You may have like multiple structs, but they generally have like some settings object that get passed into your initialize, like your init function. And that's because alternatively, I could have actually taken like every single one of these as an input to this init function, right? But because that would be too big, I can just take them as like have a struct that determines all of those inputs. So really your object is still just that GPIO address, right? So that's your GPIO library. By reading this, you can pretty much know what's happening. So first you call this GPIO init, and then you initialize a pin, and then this settings will pretty much tell you like what kind of different modes you can run it in. So it has direction. If you take a look at GPIO there, it shows you all the possible directions. Direction in, direction out, open drain. So in this case, the output is set to open drain mode. The states, all the possible states, all the possible resistance configurations. So I'm going to go over the peripherals later on, so these will make more sense later on. And then the alternate functions. These are used for, if you're not using a GPIO pin only for like zeros and ones or like very basic functionality, you would actually use it for other functionalities. And for example, you can use a GPIO pin to connect it to, for example, SPI or I2C and then talk over those lines, right? So that's how it's done. So this is an example of our libraries that are like written the exact same way. So if you take a look, we have GPIO.h, then we have GPIO.c, and then we have test GPIO.c. And this test file exactly uses that GPIO library. So you can think of test files as something that saves our asses when we, make a bug. Like when you change something and that breaks something, these tests will fail, and then that will tell us that we broke something, right? So it's absolutely necessary to have tests for your files. And you guys can just look at the test files to understand how our tests are written. If not, I can run another tutorial. Yeah, that's just important. All right, let's just go through the rest of them. So yeah, you will write tests for your modules too. I mean, seriously, do it. You can think of test files as documentation. To use a module or library, you can just look at its test file, and that test file will import it, use it. It tells you what are the expected values that are supposed to come out of that module. So it exactly tells you everything about the module. Oh, I was gonna take a look at softarmor.h. So let's just take a look at softarmor.h. And in this part, I'm gonna actually include it. So I want to just show you guys how to read our libraries and then how to like use them in your own projects, because I think it'll be pretty useful. So let's make a new project. Make new project equals using soft timers, right? So I made it this new project. So if I do ls projects, you can see, where is it? Oh, using soft timers. It just appeared here, right? So I'm just gonna make them projects using soft timers source main.c, and then let's just include log.h int main return 0, and then I want to use the soft timer library. So let's take a look at what it looks like. Soft timers.ah, boom. So always read the comments at the top. Those are the most important. So it says software-based timers backed by a single hardware timer. So what's a hardware timer? What's a software timer? Right? So these are usually things that you can ask yourself when you're reading these libraries. Then that leads you to Googling stuff, and that leads you to understanding stuff more fundamentally. Otherwise, you can just use the libraries, but then it's always better to have a proper understanding of how everything, like where every single thing comes from. And this is a lot of knowledge, right? So don't worry if it's kind of intimidating in the beginning, but it's okay. So over here you can see it looks like there's a minimum time. So I guess this is, for example, because I haven't really read this file like rigorously before, so what I'm reading is my understanding right now. So min time microseconds. This U stands for micro. So it means that the minimum time that you can like schedule a timer is 50 microseconds. And then max timers. I guess this is the maximum number of timers that you can use all at once. And then soft timer init. It says initializes a set of software timers. Clock speed should be in megahertz. Subsequent calls will do nothing. The clock speed is that of the external PLL crystal. What the hell does this mean? You don't have to understand all of it. Slowly you will. Yeah, what's up?
So like the void soft timer init, like what's it doing?
You can take a look at what it does by looking at softtimer.c.
No, but like isn't it like just like code wise? It's just like that's the only thing that there's no other subsequent libraries that have that function. It's just like a line of code.
Then when it's called or something, right?
Like
Well, softtimer init has to actually turn on the clock part of your MCU.
so is it like communicating with the drivers then?
Yes.
Okay.
Yeah, to take a look at that, you can actually take a look at here. So softtimer init, in this case, it's actually not doing the, so it basically is calling this stimers, which is a static variable that this module uses by itself, right? So it's allocating some memory and then just like setting it to 0. So up here, you probably have an stimers. Let's see. Oh, there you go, right? And then you're setting that part of memory to 0. I don't know why, because he's already used like initializing it to 0. I don't know.
Yeah.
And then he's doing object pull init. An object pull is another module that we have. It's like another library. It's basically a pool of objects. You can read it later on to understand if what it is. Object pull itself is a software engineering paradigm. So it's taking this, and then it's just initializing it, and then it calls this private init peripheral, right? And this part is actually where it actually sets the peripheral clocks. So right now there's a clock command, and then it says RCC APB stands for Advanced Peripheral Bus. TIM2 is the second hardware timer that this chip has. The STM32 chips that we use actually have, I think, 4 or 8 software timers. 4 or 8 hardware timers, and we're only using one of them.
So is this the driver then?
This is the driver.
Okay.
Yeah.
How is that connected to the softtimer.h?
Softtimer.h includes this. Well, this is softtimer.c.
Oh, softtimer.c is a C file is the driver, and then the 8. Okay.
No, the .h file is the
header.
Is the header file.
Yeah.
.c file is the implementation of your module. Softtimer is not a driver.
Oh. Okay.
It's a software timer that works on top of hardware timers.
Whenever you're using this softtimer.h, it's also using the softtimer.c?
Yeah.
Okay.
Yeah. Well, I mean, softtimer.h doesn't have any code in it. It just has like a whole bunch of declarations.
That's why I was really confused. Okay, that makes way more sense.
Yeah. So if you take a look at my last example, the person.h file didn't implement anything.
Yeah.
So you can't just you can't do anything. All the functions are empty.
I was looking at like the interrupt.h file. It's just one line of code. It's like
yeah.
That's
the declaration.
Yeah,
so if you want to take a look at the actual implementation, look at the interrupt.c.
Okay, cool.
So over here, like these lines of code are like you would have to read the datasheet thoroughly to understand these, and you don't really need to, because that's the whole reason we have these libraries for you guys not to deep dive in the datasheet. But if you're curious to know where everything comes from, which would be actually really cool, because that's what I'm doing, it would help you guys a lot. So yeah, large function just sets a whole bunch of registers. It's pretty advanced stuff. I don't want to get into it right now. So that's your .h file. And you're like, okay, now how do I use this file? Because if I take a look at .c file, softtimer.c. So first of all, there's 2 softtimer.c files. There's like x86, right? And then there's STM32, softtimer.c, right? There's the STM32 and then there's x86. What do these mean? Well, the platform parameter actually define the environment in which you're running this code, because you can run this code on Linux or you can run it on the tiny microcontrollers, right? So therefore, if you're using something like a timer, behind the scenes it needs to use different function calls or different resources to be able to like use a timer in your computer versus a timer in your microcontroller, right? Which is why we are actually using we actually have these 2 different kind of structures, right? So whenever you're curious to see how these things are implemented, STM32.1 shows you the implementation of the microcontroller, and then x86 shows you the implementation of Linux.
Cool.
So STM32. So you're like, okay, I want to use the timers, but this pretty much confuses me because it's like 250 lines and it's a lot of like weird symbols that I've never seen in my life, and you get confused. So the fact of the matter is you never need to read this file at all. One thing that you can do is to read the test file. So sorry, I'm activating Siri. Test softtimer.c, right? Boom. So this is the test file, and this test file is much easier to read. It exactly tells you what you need to do. Yeah. So
what's PRV? It keeps popping up.
PRV is a private member.
Private? Okay.
Private member. Like PRV is our naming standard for a private member function.
Okay. And so you make it private by putting static ahead of the function, right?
Yeah. This static is actually what makes it private.
Okay.
This PRV is just our naming convention, just so that we know that this is a private function.
Yeah. Right.
So as you can see, there's a setup. Like in all of our test files, there's a setup test file function, and then there's a teardown test function, and then there's multiple test functions. So every function that starts with test underscore is a test function. And then if you go down, test soft timer preempt, test soft timer. Oh, I think this has some. Yeah. So line 112, test soft timer, cancel timer. So these are all the different tests that we wrote. These are also called unit tests that test the library of soft timer. But so not only does this kind of like save our ass from like breaking this code later, they also act as documentation. So reading this file, you should be able to understand how this entire library works. So well, obviously, it's like, why does every single test underscore file, like function need to start with test underscore? Because we're using a test framework, and that framework is Unity. It's called unity.h. So if you guys ever wanted to write, for example, bring unit tests into your C projects like later on, because this one already has it set up, but if you later on wanted to do it, Unity is the testing framework that we're using for testing C++. Sorry, for C.
Is that
right?
one you've written, or is that one that's like extreme?
No, it's out there. Like you can just like go and Unity test framework.
Okay.
It's a framework for testing embedded systems. So it's pretty sick. You can actually read it. But we've already set it up, so you can run the test. But right now, the only things that you guys need to care about is that for every single test, this function of setup test gets called first. It sets the environment for your test to be performed in, and then your test runs, and then after that, teardown test runs. So you can see that this one is empty right now because there's no tearing down that needs to happen for these tests to happen. So in your setup test, you can see that interrupts are initialized and then soft timers are initialized. So let's go and copy paste them here. Right before you use them, you would have to use initialize interrupts and soft timers, right? And then this underscore test soft timer set counter function gets called. Where is this? Let's see where this guy is defined. This is for the STM32 case. So I don't think you really need to purposely start close to the rollover. Oh, so this one is just like a when you're running this test on STM32, you would have to set this for one of the tests to work. And then let's see what's happening over here. So in this case, it's a little bit the way this test is written because it's trying to test this entire library. This may confuse you a little bit, but you can actually just pay attention to the important parts, and by just reading the code, you can like start making sense of it. So it looks like there's a soft timer ID variable, right? That here it's defined as volatile, but in your actual code, you don't really need to define it as volatile. Because right now in the callback they change it, so you don't have to care about it right now. And then there's a soft timer ID, and they're both initialized to soft timer invalid timer and invalid timer because these are both of type soft timer ID, and 0 is actually a valid soft timer ID, so you can't just initialize this variable to 0, which is why they've been initialized to an invalid timer. And then the way that the soft timer works is, so look, it says soft timer start milliseconds. So I guess this actually starts a soft timer for me, right? So what if I call it? So let's see if I take a look at the definition. It takes the duration, it takes a callback, it takes context, and then it takes timer ID, right? So timer ID, I guess, is something that I need to provide. So I can just allocate a timer ID. Soft timer ID, soft timer ID. All right, I don't have to initialize it really, because after I called it soft timer, it will get initialized. And then soft timer init has been already called. I want to just start soft timer. Sorry, let me close Slack. Okay. So let's say after a second, so you int 8t, actually you int 16t, because I want to put a second equals 1,000 milliseconds, right? And then over here, what is the first thing? Oh, the first thing is the duration. So actually, let's just pass in 1,000 here instead of passing in a variable. So after a second, I want a callback to run, and then you need to provide it with the callback, right? Soft timer callback. So what should your callback look like? You can take a look at this guy, right? So this is a type def of what this callback should look like. So it's a function that is void, and then it takes in a soft timer ID, and then it takes a context variable. Sorry. So I'm just gonna define it here. Void PRV. So static void PRV. Soft my callback. So you can name it whatever you want. Let's make sure that it has the same function prototype or the same signature as this function. What's that?
When you plug in like 1,000, is it automatically converting it to a uint32? Because that's what it's asking for in the function.
Yeah.
Okay.
Yeah.
One thing.
Yeah.
Isn't like soft timer callback? Isn't that its own struct? I would say like your plastic.
It's not a struct. It's a pointer of a function. You don't see a struct here in this line, right? So this is the notation for a pointer to a function, because you can have pointer to functions.
Oh.
Yeah. Oh, maybe I should have covered it. But yeah, this is basically a pointer to function. That's how you type def a pointer to a function. So type def, and then over here, this thing means that what that function is returning. So in this case, your callback doesn't return anything. And then over here, these are the inputs to that callback. You can open that door. Hey, how's it going?
I was downstairs. I didn't know we were doing this.
I posted it on the Firmware channel.
I didn't read the Slack.
Oh, it's okay. So I've been recording this, so don't worry. So I have my callback here, right? And then in my callback, let's just do some logging. So log debug hello, right? And then let's make this happen repeatedly. So how do I do that? Let's see how that happens. So soft timer start milliseconds. I put 1,000, right? And I have to put the callback. So once you define a function, the pointer to that function is, interestingly enough, just the name of that function. So you can just put the name of that function here. What's up?
So it is in the function declaration, is it saying that you need to have a private function that's fed in?
No.
It's just okay. It's just
yeah, I just made a private right now here. Because usually whatever kind of function that you freely define in your C file,
yeah,
they're private usually. Unless they are functions that are meant to be public, right? But this is your main file, so this is not really a module. This is where all the modules come together,
yeah,
right? So you don't, like whatever you define here is not meant to be public anyways,
yeah,
right? Okay, what was I gonna do? Okay, so the second thing was callback, and the third thing is context. So you're saying, what if, so let's just not do context right now, and then I'll explain context later. And then you pass in the ID. So every time, so there's a limited number of timers that you can run at all times, right? There's 30. So every time that you run a timer, you can actually cancel it later and all that stuff. Where you're like, well, how can I cancel it? Every time that you schedule it, this soft timer start method returns, like, gives you a timer ID, right? And then you can use that timer ID to cancel this timer later on in case that you don't want anything to happen, right? So let's see what happens right now. So I have the ID. I have to pass the pointer of the ID. I passed in this function. This function happens after a second, right? So just so that my program doesn't die, let's just do a while true here, right? Because otherwise my program will exit and this timer will not go off, right? Boom, let's run and see what happens. All right, so it says, hello, my name is, wait, oh, it's not running this program. Wait, what? Ooh, I've been editing this in a whole different Vim session. So using soft timers is my thing, right? So make run project equals this, and then platform equals x86. All right. Oh, whole lot of. So yeah, if you've ever written any code, you will notice these std bool.h. So it's a system header file. Let's just do that. Oh, oops, this is an OOP example. Let me just completely close this session so I don't accidentally just. Oh, we're done with this too. We're done with this. Okay, now I only have 2 sessions. Okay, this is good. All right. So by default, true is not defined, so you would have to do include std bool.h. We're just booling out here. All right. No one got that joke.
It was funny.
It wasn't funny?
It was funny.
Oh, thank you.
I laughed from the inside.
Ah, good. And it says unknown type name, soft timer ID. That makes sense because I haven't included soft timers. Let's do that. Soft timer. And then std bool. Whoops. Now let's run it. And it says interrupt init because I have to include interrupts as well. Interrupt. And if you add every library that you're using, it may require other libraries to be initialized. How do you find that out? 2 ways. One, just reading the top of that file. It says requires interrupts to be initialized, like this line. Right? Or you can take a look at the test file. Test soft timer. So you can see in the setup test, it initializes interrupts first, then soft timers. Right? And the ordering matters. So if I reorder these tests will fail. Because soft timers require interrupts to be initialized before they can be initialized. Right? Alright, let's run this. Boom! So after a second, the hello gets printed, right? So my program is constantly running here. When your timer goes off, an interrupt actually appears. So your CPU, instead of executing the instructions over in this empty while loop, it'll save whatever its states has, jumps to this, calls this, and then jumps back here, and then keeps doing whatever it was doing before, right? So that's how this whole thing is working. Now, let's use context. So you're like, well, what if I want to, let's actually make this hello appear multiple times, right? All right, let's do it. So interestingly enough, you can make this appear multiple times because when your callback is off, you can actually schedule another timer, right? So that's pretty cool. So if I schedule another timer, let me just like declare this. Boom. By the way, your callback gets this timer ID, so you can, if you schedule multiple timers with the same private function, you can distinguish between them using the timer ID. Anyways, so let's just do the same thing. So after a second, my function gets called, and then I schedule another another timer. As you can see, there's that kind of recursive behavior here because I'm passing the function in its definition. Right, so that's a little bit of recursion magic. So now let's run this. Whoops, let's run it again. So you can see hello appearing every second, right? Now about that context. So you're like, okay, what if I want to have some state of how many times this function got called? Or like, what if I want to just pass in any kind of data inside this, right? How would I be able to do that? One way is to have a global variable. So you can have like some global, is global? No, it's not a keyword. So let's say I have something like uint 32t count, right? Let's just assign this to 0. So let's say I have some global variable, right? And every time that this function gets called, I do count plus plus. And then I want to make sure that I print it here. Let's count it before, increment it before so that we can see a nice one indexed count. Right, there you go. So let's run this again. Hello 1, hello 2, hello 3, right? But this is a terrible idea. Absolutely never you should have global variables because it'll be a shit show once you have like more than 2 modules sharing the same value, and then this is like the root source of like all sorts of really, really bad bugs. That if your code has global variables, by the way, I won't look at it. So if you have a problem, I won't look at it. I will point it out. I will tell you that if you rewrite it, I will look at it, and I will, but never have global variables. So one other way that you can do this is to have a local variable here, right? And then you can pass the pointer to this count variable as context. Right? So this context, it's a generic pointer. Void star, by the way, is a generic pointer. It can be any pointer, right? So pointer to any kind of data type. So I can actually do count, which is a uint 32t star, right? Count ptr equals, well, right now I can just set it to equal to context, but at other times you can actually be explicit and cast it to a uint 32t pointer. So if you don't know what casting means, you can actually convert some data types to other data types, and that's casting. It's basically this notation, because right now I have a void star, and then I can't just assign it into a uint32 star. So I can do this thing, and then C will say, okay, I'm actually explicitly changing the type of this context value. So now I can dereference it. Do you have a question?
Yeah.
Oh, what's it?
So can you give us like a picture of what context is in general? Because I know like FSMs uses it.
Yeah.
And, like, so what is it kind of? Is it just like a variable that will change based on how many times like it's iterated, or?
No. Whenever you have a callback function in any case,
Yeah.
right? And callback function, you only use callback functions when you want things to execute outside of order, right? If I was doing like this hello within my while true loop, then I wouldn't have a need for this context value, right? But whenever you pass in a callback to any of our libraries or any of your own code, it means that you want that callback. It's basically the source of a callback is basically an event-based programming, which is a different paradigm of programming. So event-based programming means you want something to happen once something gets called. You want something to happen once an event happens, right? How do you do that? You assign a callback to an event, and you're like, okay, whenever this event happens, I want this callback to get called. So in your browser, for example, you can set a callback on a click event, and then you can like click on that button, and that'll like call some function in JavaScript that you define. Over here, that callback can have many different implications. So here, I'm scheduling a soft timer, and I'm assigning a callback, right? So once this timer went off, that's an event. So timer going off is an event, and then once that event happens, this function gets called, right? So you can call a function based on that event, right? But what if you want to pass any input to that function? What is your usual input to the function? Your usual inputs to the function are basically its parameters, right? But what if you want to like pass in? So when you're passing an input to a function, right? You need to specify the data type, right? And then you need to specify like whatever that parameter is, right? But what if you don't know what you're gonna pass in, right? Like I could also pass in a struct here. I could pass in a struct that's 6 levels deep here, right? I'm not limited to like a simple UN32 value, right? And oftentimes in our code, you will see that those stuff that have been passed in are actually like pretty major, big, bulky structs because they contain all of the information of your application, and you may want to do something with that information, right? So this context is basically a generic holder for all the variables that you're going to pass to this function, right? Which is why you will see it in state machines, you will see it in any kind of library that we have that has a callback. Similarly, interrupts have context. Can has context because whenever you receive a message, that's an event. So you want some context to run with that callback. Whenever you have callbacks, you will have context because callbacks are generic, right? You want to keep it generic because your user should have the flexibility of passing whatever data that they want, right? The alternative would be to have a global variable and then you know that within your callback function you can access that global variable. But global variables are a terrible idea because what if you have 2 callbacks and then both of them use that global variable? And then you can have very weird situations where one callback is getting called and then some interrupts goes off. Before this callback finishes, it jumps to the other callback, and that callback changes the value of that global interrupt. So these are all just all the reasons that you should have global variables.
I have a question.
Yeah.
What's the implication of using the dereference operator for the context? Usually use the ampersand for passing the context thing.
No, you use ampersand to get the pointer. You use star to dereference it. Yeah. No worries. So I'm doing this thing, right? So I basically go and dereference that counter pointer and I increment it, right? And then you can see that the same behavior is happening here. Uh-oh, what's happening? Value computed is not used. Maybe I should dereference it like this. Oh, it just says, oh, that's because I need to pass this in here. And I need to dereference it again. There we go. Hello, 1. Oh, ooh, interesting. Some interesting stuff is happening here. So what is it that's happening here? So the first pointer is the context that got passed in, right? Right? And then the second time that I schedule this, the context is actually null, right? So it's actually very fortunate that this happened because now I can talk about it. Because you will get segmentation faults a lot. And that is, like an example of it is right now here. Because I thought that everything was working, but it's not, right? And that is because whenever you try to read from a memory location that has not been initialized, you get a segmentation fault, right? Which is the shittiest kind of error message because it doesn't tell anything about what's wrong with your program. I was fortunate enough to just find it out right now, right? Otherwise, you would have to use GDB, which is a debugger, and then step through your code until you reach that point. Or you could put like printf statements before and after and then see what happens, which is kind of a sketchier way of like doing it. I mean, it's fast and you don't have to learn GDB for it. I mean, I'm guilty of using printf debugging for a lot of my stuff. Okay, how do you get rid of this bug?
Change null.
Change the null to what?
Ampersand.
Ampersand. Yeah.
Ampersand counterpointer or counterpointer itself?
Just
Just counterpointer, because this is already a pointer,
Oh, I see.
right? So let's do it again. Boom, 2, 3, 4, there you go. So now I have no global variables, right? If I can use other callbacks with other counters, that would not interfere with this counter. So yeah.
So basically, is the program interrupting itself because it's stuck it? Because like generally, from what I know, C code runs like
Sequentially.
sequentially, right?
Yeah.
So when it gets to the while loop, like in my experience, it just stays in that while loop.
Yeah,
How are you able to get out of that and run functions outside of it?
yeah, that's an interrupt. So interrupts in the embedded world are actually, so you know how, for example, like if your program, like you have a while true loop, right? And then you run your program and you do control C, right? And that exits your program, right? What does that do? Because if your computer is meant to stay in that while loop, then that control C should not do anything to it, right? But what happens is that control C actually sends your program a signal. And then there's a signal handler within your program that gets called. So your operating system in that case, because your operating system is the one that actually handles all the signals, jumps from that main to that function because it notices that this signal came in, jumps to that function and executes that function. After that function is done, comes back in, right? So the default signal handler for control C is to exit the program. So in that case, it goes and exits the program. In the case of your embedded system, which is STM32, we're using an interrupt. So when you use a soft timer, your MCU, or like the processing unit of your MCU, keeps staying within that main while true loop, right? And then your hardware timer is actually like a physical block within your within your MCU that has a counter. It probably has like a counter register. If you guys have taken any digital courses, these terminologies will start making more sense. But that counter register constantly increments. And then once it reaches a value, one line goes up, and that line actually gets connected to your CPU physically. And then your CPU notices that that line went up, and then it goes and looks where that interrupt handler for that interrupt was. And that interrupt handler happens to be here. And I mean, it's not exactly here. There's some top-level code that calls this function. But this is basically what's get called, right? So your program constantly is in while loop, and then halfway through it jumps here, executes, and then goes back to that while loop. And that brings us to another really, really important concept, which is interrupt safety. And we'll talk about it later because I want to keep this tutorial a little bit short. We're getting into like too advanced topics, and I don't want to just like, we'll get to it whenever, like a little bit later. So this is how our soft timer library works, and that way you know how to use the soft timer library. So similarly, if you wanted to use, for example, finite state machines, you can read the same thing. Usually there's like a lot of useful comments at the top that show you like how it's initially meant to work. And then you can read these, right? And then after you read these, you can go to FSM test, or test FSM. So some of you may have already done this because this is my usual first task for you guys to figure out how this works. So test FSM, you can see that there's like states are declared here, and then there's some callback functions. So output is the callback of whenever we enter the state. In this case, this callback is getting reused for a lot of states. Whenever you enter a state, you can see it. And then you can see there's this context variable appearing here too, right? And then you have your setup test, you have teardown test, transition, and then you can like look at this and exactly use learn how our finite state machines are used. So we should not have documentation for every single C code that we write because that's highly unmaintainable and your code often changes. And keeping your documentation in sync with your code is often really, really hard. So usually you want to have test files and try and write your tests in a simple enough way such that it represents what your code is, how your code is meant to be used. Our past leads didn't really do that. I mean, to them it was simple, but they were already at like such a high level of like understanding of C. But for us, I think try and make your code as user-friendly as possible, and that's important. And every time that I review your code, I'll keep that in mind to make sure that everyone kind of understands what's happening. All right, so I think that pretty much brings us to the end of this tutorial. Oh, questions? Okay.
So in the like a test file,
Mhm.
how do you like if you're trying to check like a button is pressed,
Mhm.
how would you like assert this like GPIO state is whatever? Like how would you say that without, or do you need to use a board to actually test it?
No, you can use it in Linux because we have a GPIO library in Linux, right? And that library doesn't really change the state of any lines, but it keeps its own state. So you can, for example, do GPIO set state and then do GPIO get state, see if it's the state that you set it to.
Okay, cool.
Right? What's up?
This is like off topic, but
Yeah.
I've always been curious about this because the biggest struggle, like for me when I did Reliance before, was that things can only happen one at a time. Like, you mentioned with your interrupts, that's kind of a way to work around it. But could you achieve the similar concept of setting a timer every second using multi-threading in C++?
Well, we don't have threads here because you can't have threads. Threads require an operating system to be present. And, well, here we have like a 48 megahertz, like cute little MCU that runs stuff for us. So you can't use all the operating system's nice things that it gives you with multi-threading. So which is why you use interrupts. So you do stuff in a loop, then you have interrupts, and each interrupt goes to like a different part of your program and does something. And to the outside user, it appears that all of those programs are happening at the same time, whereas it's actually one CPU, one core, no operating system present. So actually, this is how your operating system kind of jumps back and forth anyways. I mean, it's not exactly. Operating systems are way more complex. And multi-threading actually is kind of more complex than this. I mean, I haven't done much multi-threading myself. But yeah, this is a really good way of kind of like handling your code. But yeah, it's basically advanced topics, right? And eventually you will get out of that mindset of everything happening sequentially.
I have a question.
Yeah.
Any chance you could go over enums for like 5 minutes?
Enums?
Yeah.
Yeah. So actually, let's just go over them right now. Yeah. So enums. What are enums? Enums are usually used for defining kind of like labels for the things that you have that make sense. So those labels should make sense. So for example, if I have a GPIO pin, port A and then pin 6, right? Pin is already a number, right? So I can, for example, if I'm doing GPIO set state, I can do GPIO set state and then pass in 6 as the pin. But usually what happens in the embedded world is that everything is a number, right? So your port A is actually an address, right? Or like your objects. So like let me actually show you. For example, the last car is lights because this is my go-to project for showing anything. Lights GPIO config rear. So this is a file that has all the lights, like the GPIO addresses for the different lights in the car. So you can read this, right? This is an array, right? But this is a special notation for defining an array. So instead of doing, for example, well, let me actually write some stuff here just to show you an example. So if I wanted to define a array of like 1, 2, 3, so I can do int array, and then I can do 2, and I can do 1, 2. Right? This is an array of integers, contains 2 items. This is how you define it, right? But an alternative way of doing it, which is kind of like a special syntax that the GNU also stands for GNU. So the new compilers allow you to have this cool syntax, which is like this. Now in the beginning it may sound dumb. You're like, why would I list out every single index? Why don't I just go with this, right? And that's a valid concern. However, when you, for example, in this case, right? I have this variable called, let's go to line 25. So sRear outputs, right, is the variable that I'm using. That is an array of GPIO lights, sorry, GPIO addresses. I mean, they're actually GPIO output because it contains an address and a polarity, because some of these lights were active high, some of them were active low. So I just made a struct to contain both of those information into the same place. So this array, I could have just listed out the second part. Like I could have listed out these parts, right? And then separated them by commas, right? But every time that you are using, for example, let's say you want to get the, like elsewhere in my code, I want to get the strobe lights address, right? I can do sRear outputs and then do 0 because I know that 0 is strobe, right? And then I could do dot address. This would give me the address of the strobe lights, right? Or I could do something like this, right? So imagine you're in a different file, right? And you see this in of its own. And now imagine if you see this in of its own. Which one would make more sense to you? The second one, right? Because what does this 0 mean? Like it doesn't have any meaning, right? You would actually have to go into the C file where it's actually defined to know what index 0 means, right? So you don't want to do that, right? So why is this, like, where does this name come from? This is actually an enum. So actually, let's jump to definition. This is an enum, right? So I have lights GPIO config rear output strobe, and then we usually explicitly mention that this starts at 0, and then this will become 1, this will become 2, this will become 3. So an enum is nothing but a number, right? It's basically a variable that has a number, like its value is a number, right? But it gets used to structure your program. So reading your program from now on, you don't say, for example, if I want to like turn the peripheral 0 on, so like, sorry, if I want to turn, for example, rear output left outer brake on, I don't have to memorize that this is like peripheral number 6. I can just refer to it by this. As long as I import this lights GPIO config real.h file, I will know what this is, right? So yeah, this is why you define enums. It's just for your own sanity, because it makes understanding your programs much easier. All right, any other questions? So do you guys think you learned a whole lot of stuff? All right, so from now on, because we're gonna jump into like running, like you guys being given your own projects, and I mean a lot of you already have projects, but I have not seen any code written yet. So I want to see code being written very soon. However, it is a big challenge, and your mind is initially just blank. So I'm gonna run a whole bunch of other tutorials as well to give you guys a better idea on like how to even get started with a project, because the overall architecture description of a project is also important. So I will do that in a different tutorial. But first I wanted to make sure that you guys completely understand C, completely understand object orientation in C. And this is a pretty good starting place, I believe. A lot of these topics are not gonna stick like right away, so you may have to like refer back to this video a lot. I will tag different like minutes of it so that you can, you know, just jump to that specific concept. And I will keep a page on Confluence where you can just reach out to, and there's like all these different concepts that exactly makes you jump to that exact part of that video that explains that concept, so that it's, you know, a little bit easier to reach out to. But if I were to like write down all the stuff that I talked to here, that would have been like a 60-page documentation, and you know, no one wants to read. Like videos are much better for teaching purposes. So yeah, that's it. Thank